In this video, I want to take a look at integrals that look something like this. Sine to one power of x times cosine of another power of x, I guess, times dx. Um, there's a couple different things that could happen here. One is, the nice thing is that either m or n is odd. So if one of them is odd, this is going to be substantially easier. And let me show you an example here. How about the integral of sine cubed x times cosine squared x dx. With one of these being odd, what I'm going to do is I'm going to take that one that's odd and separate out one of the signs. So I'm going to write this as sine x times sine squared x times cosine squared x dx. Okay. Now there's this one sine x sitting here, and then there's an even number of signs left, so sine squared in this case. That I'm going to convert using the Pythagorean relationship that sine squared x is 1 minus cosine squared x. I still have that cosine squared x sitting out there, and I've still got the sine x sitting in front. So that integral is equal to this one, which is equal to this one. But now I've got this nice u substitution to do, because I've got u equals cosine x, and du is sine x dx. By separating that one sine x out there, putting it together with the dx, that's precisely the du, which is the cosine for, u is cosine here, and everything else in this integral is written in terms of cosines. So I'm looking at now an integral of 1 minus u squared times u squared du, and I'm sorry I screwed up, didn't I? Because this is part of the bane of my existence here in the negative signs. The derivative of cosine x is actually minus sine x. So I'm missing a minus sign to go with that, which means there's probably another minus sign out front. So I'm missing a minus sign out front. Distribute the u squared in. Actually, I'm going to distribute the minus sign in as well. So this is minus u squared plus u to the fourth du. And now I can integrate that. So this is u negative u cubed over 3 plus u to the fifth over 5 plus a constant. And plugging back in, what was u? Right here, u is equal to cosine x. So this is minus cosine cubed x over 3 plus cosine to the fifth x over 5 plus a constant. Okay. If this problem had been one where the power of cosine was odd and the power of sine was even, then I would have done this the other way. I would have separated out one cosine, leaving an even number of cosines left. I'd turn that cosine squared into a 1 minus sine squared x, and then do a u substitution with u equals sine that time. Right? Whichever one is odd, you can split it out, and then you have an even number left to convert into the other one. Okay. In the event that they're both odd, you actually have, you could do it either way. So for instance, if I had the integral of, let's just do about the simplest one we can think of, sine x times cosine x, I can do this by letting, well, it's already, I don't have to convert anything. There's just one of them there, so I don't have to convert any more over to cosines. So I could do it this way. I could let u equal sine x, and then du is cosine x dx, and this just looks like the integral. This is the u, and then the cosine x dx is the du, and so this is just u squared over 2 plus a constant, which would be, what was u, sine x? So sine squared x over 2 plus a constant. Likewise, or I could have done this. I could have said, let u equal cosine x, then du is minus sine x dx, and I'd end up with an integral, well, that's the u, and the sine x dx is minus du, so I've got a negative u times du this time, and that integrates to minus u squared over 2 plus a constant. Excuse me. Plugging back in, that would be minus cosine squared x over 2 plus a constant. Now, one thing I want to point out here, that these don't look the same. And this is something that you're going to run into from time to time as you do a problem and you look up the answer in the back of the book and your answer doesn't look like the answer in the back of the book. Does that mean you're wrong? Not necessarily. It might be that you and the book are both right. It might mean that you and the book are both wrong. It actually might mean that you're right and the book's wrong. But anyway, one of those things is the case. And particularly with trig functions, you've got to be flexible enough to be able to realize that, hey, these can be transformed. So for instance, this sine squared x over 2, the sine squared x could be rewritten as 1 minus cosine squared x. So that whole thing's over 2, still plus a constant. And notice this is equal to a half minus cosine squared x over 2 plus a constant. But the half plus a constant is just a constant, and sure enough, that's what this one is down here. So although initially it looks like this is written in terms of sine squared, well it is, and this one's in terms of cosine squared, but they're actually equal to each other. One is just a vertical shift from the other one. In fact, you got to shift by a half to get from that one to this one. Okay. One more thing that I want to do here with this particular integral is that it can be done yet another way. For those of you who know some trig identities, which hopefully more and more of you will be learning them, I have some videos posted along with the course, just trig identities and where they come from and getting used to using them. Anyway, if I throw a 2 in here and take a half out, that stuff inside there, this is the double angle formula for sine. So this is 1/2 the integral of the sine of 2x. Usually we go the other way. We start with the sine of 2x and rewrite it as 2 sine x cosine x. But anyway, there's that identity that says the stuff inside here is the same as the stuff right there. But now this is just a nice u substitution with u equal 2x. du is 2 dx. So I'm going to need an extra 2 in there and take another half out in front. So it looks like I've got 1/4 the integral of sine of u, which would be 1/4, actually minus 1/4 cosine u plus a constant, and cosine u, but u is 2x. And then I look at that and say, does that look like the other answers I got? And the answer is no. This was cosine squared over 2. This was minus 1/4 cosine of the 2x, cosine of 2x. But again, you got to be flexible, particularly with trig. This can be rewritten with a double angle formula for cosine. So this is minus 1/4, and the cosine of 2x is actually 3 things I know for the cosine of 2x. But let's start with cosine squared x minus sine squared x plus c. And what I see here is I've got sine squareds and cosine squareds in there, which is kind of a combination of the two that I had up above. I got a 1/4 out in front instead of the halves. But I can convert it into some of those other things by just saying, let's, for instance, switch this cosine squared into a 1 minus sine squared. So I've got minus 1/4, I've got a 1 minus sine squared x, and then another sine squared x plus c. So I'm looking at minus 1/4 times 1 minus 2 sine squared x plus c, and distributing that in, it's minus 1/4 plus 1/2 sine squared x plus c. And the minus 1/4 and the c are just one big constant, so this looks like sine squared x times a half plus a constant, which was the first answer I got, right? Wasn't that the first answer I got? Or was that the second one? That was the second answer I got. Yeah, the first one I did was right there. sine squared x divided by 2 plus a constant. So there's several different ways to do this problem. They all end up with different looking answers, but they're really the same answer. Okay, and be ready for that. Just because your answer doesn't look like the back of the book doesn't mean you're wrong. You got to do a little bit of algebra, a little bit of trig to see if you can get yours to match theirs. I would suggest that if you can't, or you're having trouble trying to match them, at least let your calculator draw a graph of the book's answer, let your calculator draw a graph of your answer, and see if one is just shifted from the other by a constant, or if they're in fact the same graph. Right? Anyway, what we need to look at now is if the powers of both sine and cosine are even. So if I had something like sine squared x times cosine squared x, there's two options here. The book highly suggests that we use the power reducing formulas. So that on something like this, I would write this as 1 minus the cosine of 2x over 2 times the power reducing formula of cosine, which is 1 plus the cosine of 2x divided by 2 dx. And just multiply it out. The half and the half become the 1/4. I'll write it out in front here. And then you FOIL that out. So 1, actually in this case, the outsides and the insides cancel out. And I'm just left with minus cosine squared 2x. I can integrate the 1 easily enough, but this thing I'm still going to have to do another power reducing formula on it. 1/4 the integral of 1 minus, and this would be 1 plus the cosine of 4x divided by 2 dx. And now that can be integrated. Okay. Actually, I'm not going to integrate it quite yet. I'm going to distribute the half through because this is 1 minus a half, so that would be a half. And then I've got minus a half times the cosine of 4x. So actually, let's factor the half out as well. So that would be a 1/8 out in front. And then that would just be a 1 that integrates to x. This would just be a cosine of 4x, actually minus cosine of 4x, which would integrate to minus 1/4 of the sine of 4x, right, plus a constant. So that's the way the book would do this problem, and if you had other even powers of sine and cosine, then you would just do this thing, but maybe this was squared if that was a sine to the 4th power, or if this was cosine to the 6th power, this would be this thing cubed. And you just got to multiply the whole dang thing out, and then you're still going to have big powers of cosine, so you got to break them down again. Personally, I would say use the telescoping integrals, right? For instance, on this one, if I had the integral of sine squared x times the cosine squared x, I'd write the cosine squared x as a 1 minus sine squared x. So I've got a sine squared x times 1 minus sine squared x. And then you can write that, distribute that through. You've got sine squared x minus sine to the 4th x. Right? The sine squared x you can probably handle with a power reducing formula, but the sine to the 4th x, I would go and use the telescoping integral way back up here somewhere. Where do we have those telescoping integrals? Yeah, right here. So the sine to the 4th x, this would be a 4, this would be a 4, that would be a 3, that would be a 3 and a 4 and a 2. Right? And then you can integrate that sine squared using a power reducing formula. I think that's probably the easiest way, particularly if those even powers of sine and cosine in this integral, where are we? Where are we? This integral right here. If these things are big, 4 and 6 or something like that, this just gets big and ugly to try to multiply all that out. And I would just go with the switch it all into sines or switch it all into cosines and use that telescoping integral for sine or cosine. Anyway, there's integrals with powers of sines and cosines.